Okay, let's summarize what we discussed in the first session today. I think I should take off this. So, in terms of physics or mathematics, the first session we're talking about subsurface response, which means seismogram. Actually, we can treat it as a black box because we don't know exactly the velocity, exact density, exact properties, right? But there are two fundamental assumptions. We assume it's time invariant, which means if you acquire a data last month today, and then you require a second time today, you can compare the two data sets without any problem. We do not assume any significant changes between these two dates, so time invariant. Secondly, these two data sets, last time we did acquired and today acquired, you can simply sum them together. Maybe just sum them with a different weight, but fundamentally they are linear. Okay, so for example, if last month this day you acquire data, you think the signal is too weak, and today you acquire the second time, and you can sum them together, make average. So basically, the amplitude is average. That's basically linear. So there's two fundamental assumptions. One is the time invariant and linear. Okay, that's the thing. Secondly, as we said in the model, every reflection is a copy of instant disturbance, which means the wavelet. Right? We are talking about detail in the second part about the wavelet. Wavelet, in fact, is we call the filtering. It's not the spark. Even you have a seismic source of spark, but you record it's not a spark. So basically, it's a filtering. You can mathematically treat it as a filter. That's the wavelet, and the result, as we said, straightforward physically to understand it is a superposition, but mathematically, in terms of computing calculation, it's convolution, or mathematical convolution is convolution. Okay, this is the concept. So this is basically the summary of the first session. Any questions before we move on? All right. Okay. So thank you for you guys attend the applied geophysics. So this seems quite straightforward. So now we just try to cover some background knowledges. First of all, we try to review the signal processing theory. As I said, the core or the fundamental theory here is Fourier transform. So it's called Fourier Theory, right? Fourier Theory means we represent any signal, which means in this case any seismogram or any seismic waves, as a sum of sine, cosine functions, right? So that's the fundamental. So each cosine or sine functions, each of those have special properties, which is because cosine or sine are periodic. So they have a fixed frequency. Frequency means how many circles per time unit, right? In this case, how many circles per second. They have a special physical unit called hertz, which is 1/second. Okay, so have a constant frequency for the cosine or sine wave, and a constant amplitude for each individual cosine sine waves, and the constant phase. We're talking about detail. What is phase? Phase really means time delay. Okay, but the phase came from the calculation. When you do the calculation of complex value, you have a modulus and the argument, which is an angle, which phase, called phase. Okay, but in terms of the straightforward physics, that's time delay. phase came from the complex calculus. Okay. Right. Why we said Fourier transform is a fundamental theory because this will simplifies our not only for the explanation, but it also simplifies our life. For example, when we're talking about convolution, I already had a difficulty to say, how the superposition becomes a convolution, right? That's real difficult. But here, even when you do the calculation, that will be even more complicated. So it's better use a Fourier theory. You transform this into the sine, cosine functions, and they have amplitude constant, the frequency constant, the phase constant, and then you can do the simple calculation, which is that amplitude, they multiply each other, and the phase, they sum each other. You sum two phases, sum the amplitude, right? But of course, for the same frequency, right? For the single frequency, you sum the amplitude, and multiply the amplitude and sum the phase. It's simple as that. That's the convolution. So let me repeat. After Fourier transforms, the two-time series becomes two frequency time domain, frequency domain representation, right? So the convolution becomes the multiplication of two amplitudes and the sum of two phases for each individual frequency. Okay, that's the easy. And another thing, similar to convolution, but seems much straightforward, is called correlation. That's important for us. If we have one seismic trace correlate to another one, if they are similar, right, we can see, okay, those similar components are the signals we're trying to keep. Some part is not similar, so not correlate. We try to improve that by remove some noise or enhance some part. That's correlation. So correlation is also important tool for us for example, if we want to track the horizontal coherence, horizontal reflections, right? We try to work out the correlation. Nowadays, we can do the correlation for what? For detect fault of subsurface. In the seismic cube, you have data, right? You have trace by trace, and then you do the correlation. If they are very highly correlated, that's fine. If they are not correlated, have an anomaly in terms of correlation. That's the very good indication of a fault, right? So that's the correlation also. In terms of correlation, how in the frequency domain after Fourier transform, they're actually amplitudes, they are multiply each other, and the phase, instead of a sum two phases, but they subtract two phases. That's the correlation. You can see after if you mastered Fourier transform, you can do the convolution and the correlation. Very easy, very straightforward, right? Efficient as well. Now, before we talk about theory of Fourier transform, now let's go back to very fundamental method called the Z transform. So that means if we understand this, you can, even you didn't learn Fourier transform before, or even you learn the Fourier transform in terms of integral, but you didn't learn the discrete Fourier transform. I think here, this few slides can help you to understand that, okay? First of all, we're talking about Z transform. What Z transform means here? Okay, let's assume your seismic trace is digitized. Of course, digitized nowadays, right? Everything you import to a computer, they must be digitized. So you have this bold font here is a vector. This vector is composed of A0, A1, A2, A minus 1. So that means we assume this time series have n samples, and the indication index from 0, 1, 2 to n minus 1, total n samples, right? Okay. So what is Z transform? Z transform, instead of a time series, we transform this time series into one function, single function, polynomial, single function. So here we call it AZ, capital A, Z. So for how we make it that? For each individual sample here, we use A itself as a coefficient, weight, let's say co-weight. And then we use Z here with the power, Z power 2, Z power n-1, Z power here, Z power 0, Z power 1, right? So the power of Z is the index of time. And the coefficient here is the actual sample. And you sum them together. That's called Z transform. Straightforward, easy, right? So you can see A naught, Z naught. Z naught is 1, right? A1, Z pi 1. A2, Z pi 2. N-1, Z pi 9, right? So mathematically, you just sum them together. So basically, the coefficient, which is the amplitude of a sample, and the Z power of index here, K. Okay, this is Z transform. Easy, isn't it? So math is very easy compared to what you study here, geophysics. Math is much easier, but you do need to understand the physical meaning behind it. So in terms of Z transform, we can the physical meaning here. The coefficient is the actual sample amplitude of samples, right? And the index of Z, the power of Z is the index of a sample. Remember, index of sample, okay? It's do not be mixed with 0, 1, 2. Here happened, just occurred. A0 is at time 0, A1 time 1, but maybe not necessary, right? We can see later. Right, to understand the Z transform, let me show you one more mathematical question here. AZ, in the previous slides, we multiply by Z, just see what Z means, right? So if we multiply that with AK, it was ZK, right? But now multiply Z becomes ZK plus 1. You see that? That's no problem, okay? If we expand that, instead of original AZ, but now have A0Z, A1Z square, and we have a first term here, Z0, which is Z power 0, which is 1, right? So the coefficient here is 0, you can see that? So new series become 0 in the front, A0, A1, A2, A, and minus 1. You can see that the length longer, it was n samples, no, it's n plus 1, because we have 1 in the front. Because you multiply by Z, which means your whole time series from A0 to A1 shift rightwards. Yeah? So Z really means a unit time delay. If you multiply 1Z, you shift this one to time delay. So you remember A naught was here, right? If we're talking about this index time 0, but now it's moved rightwards. Yeah? Okay, that's for single Z. If we multiply multiple Z, for example, Zn here, it becomes, the polynomial becomes AK Zk plus n. If we expand that, you can see in the front I have n zeros, and then A0, A1, A2, An minus 1. So multiply Zn means you time shifted by n zeros, right? Right-hand side. If we have a negative, of course, shift towards left-hand side. So again, that is a unit delay operator. That's straightforward, right? So easy, mathematically easy, and physically also easy to understand. Yeah? Have you learned this transform before? No? That actually leads to the Fourier theory. Okay? Now, first of all, we use the Z transform to lead to the, as I said, convolution. Right. If we have a two-time series, one's A, one's B, after Z transform, we call it AZ and the BZ, right? Now, we just simply multiply the two series. in the Z transform domain. So this one, remember, is AK ZK. This time series has n samples, capital N. This time series B has m samples. If we multiply these two, you do the simple manipulation, you end up, here you just, because this is a polynomial, you can simply put them together, right? So K from 0 to n minus 1, and error from 0 to n minus 1, right? Okay, you have AK, B arrow, zeta. Now you do the index here, you have 2, right? I mean, you remember when we're talking about the Z transform, the very important information is from the power of Z, right? But here, power of Z is K plus L. It's somehow slightly complicated. So what we do, we just try replace K plus L with a single variable, which is P here, right? If we assume if we set K plus L equal to P equal to K plus L, so here K unchanged, but L here becomes P minus K, right? So you end up with this formula here, AK here, AK here was BL, L equal to P minus K, so you have the AK P minus K, and a ZP. So now we have a new time series. The index is P here, right? Index P here. And the coefficient of each Z factor, this is coefficient. You see that? This is summa, is coefficient. So this, which is simply called CP. So CZ equal to AZ multiplied BZ, eventually becomes the summa of CP and ZP. You see that? So new time series, you have a CP as a coefficient, and the P is index. That is convolution. So that is convolution. So convolution, just what you learned in your math course. What is convolution? Convolution means one time series multiplied by another time series, but in the inverse order. This K here is minus K. You see that? And every time we shift by P from 0 to where? In the previous slides, actually to almost double the length, right? Minus 1. Okay? That is convolution. You learned the convolution before. I'm sure you learned that. However, if we learn the Z transform today, you can see how easy. Fairly easy, isn't it? You just do the transform A, transform B series, and then you multiply them. You end up with CZ. And then, of course, when you have CZ, you have an index. From the Z power, you can find the index. And then you can replace, you can just put all the coefficients into series, right? So you end up the new series. So now, that was the Z transform for convolution. We derived how to get a convolution formula. But now, we try to link the Z transform to what you learned, Fourier transform, right? You learn the Fourier transform, typically for the discrete Fourier transform, you're very likely to discretize the integral, which is continuous function, into discrete formula, right? But in fact, there's some properties involved. Actually, derivation should not simply discrete that, should form here, because there's some assumption there we will point out, right? Now, as we said, what is Z? Z was unit delay operator. Now, if we use unit operator delay, I think I mentioned before, the phase is also called time delay, right? Now we have time delay, unit time delay, which is delta t. If we're talking about put the time delay into phase, you remember phase means in the complex value, we have amplitude, which is modular, but we also the pure phase, right? Pure phase is E, I, omega t here. That's in your polar coordinate, right? And omega, that's because you have a 2 pi angle variation. But in our experimental physics, that's actually led to the frequency, which is 2 pi f. 2 pi f equal to omega. So you end up this formula here. Right, that's related to phase delay, the time unit delay into a phase. That's the phase. So now, if we replace the Z transform before the Z, you remember it was AK, ZK, but the Z is equal to e power of minus I 2 pi f delta t. You put here, that is DFT, discrete Fourier transform. Okay? Easy, right? Now, because we assume everything digitized, not only time series, but also frequency after Fourier transform, all digitized, right? So now we just see what we actually have in your computer software. So now that's the formula we got before. So if we know exactly delta t equal to total receiver, total recorded time, which is a capital T, and we have n samples, so digitized into n samples. So delta t equal to basically delta small t equal to capital T divided by n. So you can just simply replace this delta t become t divided by n here, right? Now, so this function, of course, that's just a time sample become digitized, but the frequency still continues, right? So now you say, okay, because everything in the computer, frequency also be digitized. So now we just digitize the frequency becomes Fn equal to n sample multiplied by delta f. Delta f is a frequency interval. And then you end up this formula. You just replace smooth f become by delta f divide multiply n here. You can see that. Okay. Now, how to define delta f? Delta f actually based on the Fourier theory. That's called a sampling interval in terms of frequency. It's 1 over the time t. 1 over time t is the total length of time duration of your signal. Okay. So if now you replace capital T here by 1 over capital delta f, sorry, delta f here by 1 over delta t, so t and t canceled, you end up with this formula, right? So now this formula, very good because there's nothing to do with the delta t, as long as your delta t is a constant. That's why the Fourier transform, if you have a single Fourier transform software, you can apply to anywhere, right? As long as the sample interval is constant, because there's nothing to do with the delta t. And you do not need to worry about delta f, because there's no delta f, right? So you just end up the sampled series. So you from one time series to another time series. Remember here, just a single function at the beginning when we talk about zeta function, we transform. Well, let me repeat it. When we do the zeta transform, we transform time series, which is n samples, into single function, right? So that's the f here, smooth function. But now we digitize f into a series digitized frequency. So now basically we go back to series again. But this series is in the frequency domain. From the previous series in the time domain, now becomes a series in the frequency domain, right? So this is straightforward. Okay. Why this one's modern day is even more attractive since 1960? Because here we have 2 pi elements here, and here all are integers. If we remember, when we do a Fourier transform, we said there's sine, cosine functions, right? One of the periodical properties is this here. If 2 pi, sine 2 pi is 0, right? How about sine 4 pi? 0 again, right? And 6 pi, again, right? So that means you can, because this same for 2 pi, 4 pi, 6 pi, right? So that means you not only worry about AK, if plus 2 pi, plus half n, or 2n actually, exact n times, capital N, it's same as AK, right? So that means you can keep not only AK, but AK plus a constant together, because then you share the same operator, right? So that's called folding. So basically, if we're talking about, for example, just straightforward, give you one example. If we have time series 1024, 1024 samples, what do? You just fold in that. So basically, the first one multiply plus the 512, right? They can share the same operator. You fold it. So original time series 1024, you can fold them into 521, and they can either further folding to half, which is 256, further folding 128, further folding 64, and further folding 32, and so further folding 16. Come on, further folding 8, 14, and then 4, right? And then 2. So doesn't matter how long your time series is, you can calculate only end up 2 operations. That's called a fast Fourier transform. You didn't learn that because you're talking about integral, but if we use DFT, discrete Fourier transform, every computer software package you have something called fast Fourier transform. So that's, you almost ignore the time for the calculation. Doesn't matter how long, right? I just give you one example, 1024, but I maybe another 10 power time higher, right? So that's the beauty of this methodology, okay? As usually, for you, let's say 5-10 years ago, I did teach a course for the second year student called time series analysis. What do we do? Mainly try to generate the fast Fourier transform. It's very easy, okay? But for your guys, the third year, fourth year, you already have enough knowledge so you can see how easy it is. So based on this periodical here, so you can share the operator for this complex number, which is cosine. You know this complex number here, which means cosine plus I sine the phase, right? Yeah. So this is share that. Now, okay. Now we're talking about already talking about DFT, also fast DFT, which is a fast Fourier transform, usually called FFT. And another thing here, actually I just didn't mention that. Here we have a minus, but this for the forward transform. But if we based on this, we can come back to the original time series. That's called inverse Fourier transform. You simply change the sign from negative to positive. The same software, you can do the inverse, right? As I already said, the fast Fourier transform for forward, which means from time series to the frequency series. But exact same, identical calculation, but only change this sign here in the front. You can work for the inverse, which means for frequency series to time. So now, the time series and the frequency series, they are identical, right? Either you can do the time transform to frequency. See which way easy for you for calculation you can do, right? You can transfer frequency series into time series to frequency. They're all the same, identical. In terms of calculation, you just find which domain is easy for you, right? But that's the Fourier transform series. All right. So let's summarize the Fourier series here. first of all, the signal, any signal, not only seismic signals, any signal can be represented by a sum of a cosine function plus I sine function. It's complex value, okay? And this sinusoids usually defined by, not usually, I mean are defined by three key parameters. One is frequency. For each individual sine or cosine function, sinusoid is a constant frequency, which is a constant periodical property, and the amplitude and the phase, right? So for each frequency, you have a corresponding amplitude, corresponding phase. So this gives us so-called frequency spectrum. What does frequency spectrum means? You have one axis called frequency. Another axis is amplitude. We call it amplitude spectrum. But if one axis is frequency, another axis is phase, we call it phase spectrum. Basically, the frequency spectrum is complex value because one axis is frequency, another axis is complex value. But complex value you learned from high school, right? Complex value can tend to the modulus, which is amplitude here, and the argument, which is phase. Yeah. So that's the spectrum. So this is very important for us. We call it spectral analysis for seismic data. If we acquire the data from field and you want to know the properties, you do straightforward fast Fourier transform, generate spectrum, see the amplitude, which was stronger, weaker, which frequency is stronger, which frequency weak, or which frequency band, which means within this frequency range, you have a visible or useful amplitude, right? Or the phases, whether this is delayed or ahead, that's the difference. Now, I already said that. So basically, frequency Fourier transform gives us an amplitude and a phase at all frequencies, right? So that's called a spectrum. Although the calculation is in the DFT, which is discrete Fourier transform, but this gives us we call it continuous data, right? Which means actually in the field it's continuous. Only because we use a computer, we digitize it, right? It's not, although we call it discrete, but it's not discrete. The physical signal must be continuous, right? Now let's show you the spectrums. As I said, spectra, not spectrum, spectra. So we have the amplitude spectra, phase spectra here. Let's see the first one here. That's basically the real part of the signal. We just call the sinusoids, but it's cosine function here, right? Okay, here, we just assume this unit here, from here, the scale is 1. So you can see this is a single frequency. Right, from here to here, in terms of time, it's 1 second. The frequency is how many circles per second. So from here to here, can you have a quick account? How many circles? One peak from here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and half, right? Something 12, 12 and a half actually. Because from peak here to 1 to 12 and a half, otherwise to here, right? So now, that's for this one. So that's time series. After Fourier transform, we have frequency axis from 0 to 100 Hertz. So here for this one, the amplitude at a frequency, what? That's 50. That's 50. That is 50, right? Here, which basically that's 25. That's 12 and a half. So only at 12 and a half Hertz, you have amplitude we call the 1 here because of the scalar here 1, right? But the next one almost same. are not almost same. Actually, the next one you can double the number of circulation, right? So this if we count that, it becomes 25. So at 25 hertz here, you have amplitude. This amplitude halved if we compare to the first one in terms of scale. It's halved. You can see. At this frequency, 25 hertz, you have amplitude. Other frequencies, they all are zeros, right? Because they only have single frequency here. So amplitude are zeros. The third one here, you can see the scale here, identical to the first one. So the amplitude is definitely same, right? In terms of frequency, they are also same. So also 12.5. Okay. Now, how we distinguish the first one and the third one? The amplitude same. In terms of frequency spectra, they are same. So we need to use a phase. Right. Now, phase, how to define phase? In this first one, at time 0, remember phase is EI 2 pi f t, right? Phase 0, cosine 0 equal to 1, right? So cosine 0 equal to 1. So phase is 0 because here's 1. So at 12.5 hertz, your phase 0. Here's middle 0. But this one, at time 0, cosine equals 0. What's the angle? What's the phase? It's half pi, right? Cosine 90 degrees is 0. And this one becomes negative half pi because we will see sine. We can find out because sine is at 0, right? So that's the phase. So now, amplitude gives us the magnitude. Amplitude spectrum gives us the magnitude of homogeneous, not harmonic function, right? And the phase gives us the time delay. So basically, this same thing, but just delayed minus half. Actually, it's not delayed, it's advanced, right? Because we delayed half pi, which means advanced half pi, right? Basically, this one here, this peak compared to this peak. So it's advanced, okay? That's why we usually call time delay. So that's why you can see the signal form, right? So phase and the amplitude. If we know exact phase, exact amplitude for all frequencies, as I said, we can use a FFT, fast Fourier transform, to reconstruct the original time series, right? That's it. So now let's see what's the amplitude and the phase in terms of Fourier theory. That is one wavelet. We call it wavelet. Wavelet means the available amplitude in a short period. That's after Fourier transform becomes this diagram. So that's low frequency gradually to 30 some hertz, right? So each of this, the low frequency means within each time period from negative 0.5 to just one period, right? One second. So one of that is a frequency, okay? So from this one, you have only amplitude here, and that one have a peak here, trough here, peak here, trough here, peak here. That's a 2, right? And the third one, 1, 2, 3, right? But this sum of together, this means we decompose this signal into so many different frequencies. How we do decomposition means we use this signal to correlate to that. The amplitude is this one, right? So this decomposition, which is Fourier transform, means decomposition. We decompose a seismic signal into a series of sine, cosine functions, right? Most likely we just show cosine function here because sine It's imaginary, and they just have a 90-degree phase shift. Cosine and sine, right? Cosine 1 equal to sine something plus half pi, right? So now, if we sum this together, only this bit, every peak here enhance each other. You can see that's a peak here. Otherwise, if here, you somehow cancel each other. So you have almost zero, but not exactly. But nearby you have something. So you do not have a spark, but you have a band-limited spark. We call it wavelet, right? Now, talking about convolution. Remember, when we're talking about convolution, this we derive by Z transform, and then in the Z transform domain, it's simply a modification of two Z polynomial. And then remember, we can replace that by time unit delay operator. We can discrete Fourier transform. So now we can, in the Fourier transform domain, convolution becomes a modification of two Fourier series, right? We already learned this. Now we're talking about phase and amplitude, how we use this formula, right? So let's see more examples before we talking about that. Why we do need a modification? Because we try to enhance the signal or remove something we don't want, right? Now, one of the objectives for seismic processing is try to enhance the resolution or increase the bandwidth. The definition of the actual physics bandwidth and the resolution relate to the Earth's convolution model. Whether you convolve with a wide span, wider bandwidth wavelet or narrow bandwidth wavelet will have different seismogram, different seismic traces, okay? And so controlled by the wavelets, which shapes the reflectivity. So ideally, the optimum resolution is when the wavelet is spark. Just like the model, if you remember, when we have an interface, we have a spark there. That's the ideal situation. But in the field, we do not have that ideal seismogram. What do? We try to somehow remove the wavelet effect, recover the reflectivities. That's the processing. You can see that? Yeah, because the modeling, which means convolution, as the supervision is convolution. So if we were trying to remove the wavelet, we call it deconvolution. Basically, we try to remove that, right? Which is the inverse field. Okay, so in practice, we never get a spark because we have some limited bandwidth. So that's always be band limited. That's called single function. Single function means wave spectrum have not from a 0 Hertz to the infinity high frequency. We always have band. After the inverse Fourier transform, you have something called single function. Single function is a sine function divided by the argument of sine. You learned that before, okay? So we try to get the highest bandwidth when we have a most frequency percentage. Let's show you an example here. Ideally, well, this from 0 to 250 Hertz. Well, that's because we cannot have infinity because your time series has a limit, have a fixed interval, okay? So the maximum frequency Hertz depends on your time interval. In this case, we will see the formula next time for how to work out this one. But anyway, from 0 to 250 Hertz, you have almost a spark, but of course, not an exact spark. But if you have a 8 to 90 Hertz, you have a look like this. That's called a single function, quite similar to the spark, but it's not exactly. And if the bandwidth reduced to 8 to 70, the wavelet becomes even wider, and 8 to 30 much wider, right? So that's the effects of wavelet. Right. here have a two diagram, same from the same subsurface model, and here for single seismic trace, repeat the plot just for the visualization, right? For number of times, 10 times, right? And the same one, but the dominant frequency different. One's 30 Hertz, one's 80 Hertz. You can see this one, you just simply have a two layer, straight like two layers. But if it's a high resolution, you can distinguish this strong one, but the weak one here, the strong one, or maybe have other layers. You can see the resolution is important for us if we want to interpret thin layers, right? So one of the objectives for seismic analysis is try to improve the bandwidth, improve the frequency, which means improve the resolution. So that you can identify the subtle changes of subsurface or thin layers, right? That's the process. Now, we're talking about, we have already talked about the frequency and the resolution, the relationship, right? The bandwidth of frequency or dominant frequency related to the resolution. But now we're talking about the phase related to the resolution. Okay, because after Fourier transform, we have two important components, right? One's amplitude and one's phase. So the phase here, when we try to do geological interpretation, we try to see if the peak of the wavelet in the same place as the interface. That would be easy for us to do the geological interpretation, right? So phase also important for interpretation. So wavelet, when you have a highest resolution, of course, it's spark or band limit spark. It's not exactly spark, but it's a band limit spark. Okay. So when the spark or band limit spark is symmetrical at t equals 0. So this phase, if it's symmetrical, we call it zero phase. We will see why it's called zero phase. Okay. So Fourier transform a spark at a time 0 is a zero phase. So what we try to do, data processing, one of the steps or number of steps, you try to change your data from non-zero phase to zero phase. So that means easy for you to do the geological interpretation. Okay. Sometimes called phase deconvolution. So optimal wavelet is zero phase. Let's show you why zero phase is good for resolution. For example, here we saw this before. If we sum this together, we have a zero phase here, right? So now, if the subsurface depths here, we can easily identify the depths. That's the zero phase, right? If the phase is linear with the frequency, you remember, when we talk about zeta operator, it's a EI omega delta t. Delta t is constant. Omega is 2 pi f, right? If it's linear with f, we do not change. We only change, which means we change the delta t with a multiplied by a number in front, right? But 2 pi f unchanged. Okay, so that means even you have a linear phase with frequency, your wavelet does not change because you only have time shift. Time shift does not change the phase. You can see if all this move to upwards, move same constant, every frequency you move by here, in this case, negative 200 milliseconds, all move them, you sum them there. Same one, right? However, the same one as before. However, if you have a phase change, in this case, each of these have a 90-degree phase change. From here to here, you can see this is no longer symmetrical. But a 90-degree means you have a peak and a trough, they are identical. It's 90-degree phase shift. This one is very difficult for you to do geological interpretation because you easily interpret this peak, one layer, the trough, another layer, right? That's cause confusion. So it's better the processing to generate the symmetrical wavelet, which is 0 phase. So that's the importance of phase. Okay. So now let's talk about. We're already talking about frequency and the phase. I think let's finish a few more slides before we have a break. Let's talk about this one. What we said before, we treat the subsurface as a black box because we don't know everything. We don't know velocity. We don't know the frequency, density. So we assume it's linear and time invariant, right? So now we treat seismic data here as in the Z-transform domain as a modification of wavelet and the subsurface structure, plus, of course, some noise, right? So this assumed the model assumed, and what we assumed, because of superposition, in terms of mathematics, we call it convolution, right? In the Fourier transform domain, we can do modification. Fourier transform in this lecture we just saw is equivalent to the Z transform. So in the Z transform, we just simply do the multiplication with Z transform, right? So Z transform is sample data, yeah? Now, let's show you this diagram before we have break. So in the time domain, you have a reflective series. If we recall that model I show you have different layers and different travel time because of a different velocity layer, right? So you have a time series. And the convolve, use this star here as a convolution operator. Convolve with a wavelet. Ideally the wavelet is symmetrical, which is 0 phase. If convolved, but also have some background noise, abandoned noise, and then you convolve plus this one equal to this one, right? So this is a time trace, a seismic trace. That's called ST. In the Fourier transform domain, we have a time reflectivities here. After transform, we have a frequency instead of time, frequency and amplitude, right? What's the phase of this? The phase we do not care about because at the moment, the phase really reflects the different time, okay? So that's the amplitude. Multiply, because in the frequency domain is multiplication, right? Multiply to the amplitude of wavelet. As I said, the wavelet is not spark. Spark means from 0 to infinity hertz. They are the constant amplitude, but now you have a band limit. So band limit means you have a lowest frequency, highest frequency, right? Band limit. If you multiply them, becomes this dashed line. Multiply, end up this. Of course, have some background noise. The background noise is random. Random means we call the white noise, which means each individual frequency corresponds to different color, but all the colors, if we have all colors, that's called white noise, a white color, right? White color, so this is called white noise. So basically, in the frequency domain, your seismic trace becomes the band limited seismic data, and of course, plus noise, right? So you can see this shape quite similar to the wavelet, right? This also gives us the way to estimate wavelet. If we have a seismic trace, you do the Fourier transform, this shape identical to the wavelet. You see that? And then we can, if the wavelet is a 0 phase, we can recover 0 phase amplitude. Yeah? So this is the way. So before we finish, let's just show you one example here, how to do the acquisition. Actually, when you watch that, you can enjoy your time break.
Save on every range. Get fast delivery And now, big sofa set.
Sorry about that.
Seismic imaging, sometimes called reflection seismology, is an exploration method that estimates the seismic characteristics of the Earth's subsurface. The technology measures reflected acoustic energy waves and is mostly used for coal, oil and gas, and geothermal exploration. Seismic imaging provides geophysicists and geologists a method of mapping the subsurface structure of rock formations. Geophysicists and geologists interpret the data to map structural features that could potentially contain minerals, hydrocarbons, or hot rock resources. The Earth's upper crust is composed of many layers of rocks and minerals that all have different properties, such as hardness, density, and porosity. The placement and orientation of these layers give clues as to the likelihood of finding mineral, hydrocarbon, or hot rock reserves nested within them. Changes in properties between different rocks can cause reflection and/or refraction of sound waves. Seismic imaging works by sending acoustic energy waves created from a sound source through these layers and then recording how long a reflected sound wave took to be received by a microphone. This data tells geophysicists and geologists where rock properties change, thus helping find oil and gas deposits. Typically, there are two methods for producing the source sound waves. One is by using a vibrosize, and the other is by using an explosive detonation. A vibrosize is also known as a thumper or a shaker unit. It is a large hydraulic ram that is fitted to a special truck. The operator stops the truck at a location where they would like to generate a signal and uses the vibrosize to ram the ground, thus creating a series of source waves. Microphones, called geophones, that have been specially placed in an array around the survey area, pick up the reflected sound waves and record that data to a digital medium for later computer analysis. Sometimes, instead of using a vibrosize, explorers will use an explosive like dynamite to create the source wave. Explosives are placed beneath the earth in shallow drill holes. When the explosives are detonated, an acoustic shock wave travels through the ground and is detected by an array of geophones that have been previously arranged. Because scientists know how long it takes for sound waves to travel through and bounce back from different types of rocks and minerals, careful interpretation of seismic data can give geophysicists and geologists detailed cross-sections and three-dimensional graphics of the subsurface of a surveyed area. This can help them find mineral, hydrocarbon, and hot rock resource deposits.